Hi everyone, Quiveen here from the comfort of my kitchen. In today's video, we are going to briefly talk about dark matter and dark energy and modified Newtonian dynamics. But unfortunately, I won't be able to show you any of those things. Dark matter and dark energy, if they exist, cannot be observed normally. Dark matter and dark energy only interact with normal matter in the form of gravity. Gravity, the gravitational force, is the only way that dark matter interacts with matter, if it exists. Modified Newtonian dynamics are just a different way of describing physics. Newtonian dynamics and Newton's theories of physics are the ones that we normally use, and they do generally work. But in some cases, the physics as we understand it doesn't explain what we see in space. So in the previous video, we talked about Planet 9 or Planet 10 or Planet X, whatever you want to call it. And we talked about how this planet was used to explain the behavior of small objects at the edge of the solar system and the orbits of planets like Neptune. When there is a unknown thing in physics, sometimes the most realistic explanation is that we've missed something. For example, when Uranus's orbit didn't behave the way people expected, a good possibility, a good potential explanation was that there was another planet out beyond Uranus whose gravity was influencing Uranus. And based on that theory, people looked for another planet, they found Neptune, and that solved the problem. Of course, there were peculiarities with Neptune's orbit, and so the search for another large planet is still ongoing. Of course, we don't know if we find another large planet, but it is the most likely solution. When we look at other galaxies, things get a little bit stranger. So this is the Whirlpool galaxy. It's a fantastic example of a galaxy. It's known as a grand design spiral galaxy. We're looking straight down on it here and we can see the arms of the galaxy. Now this galaxy is rotating. Galaxies do rotate. And here in our solar system, we have our spinning sun in the middle. Around the sun, a disk of dust and rock and ice slowly coalesced into the solar system we have today. And we're all very familiar with the different orbits of the different planets. Mercury, right next to the sun, gets around in just 88 days. Neptune, way out at the edge of the solar system, takes over 100 years to orbit the sun. Based on our understanding of physics, the laws that Kepler put forth explaining orbits, that all makes sense. And looking at a galaxy like this, you might expect that the objects closer to the center are orbiting faster than the objects out at the edge. You'd expect the center of the galaxy to spin faster and sort of drag all of this material around it. But galaxies seem to spin at a pretty consistent rate. The arms of the galaxy and the core of the galaxy almost act like one large plate spinning around together. And that just doesn't make sense. According to basic physics, that's not what should be happening at all. We know that galaxies have a lot of mass. Galaxies are huge, heavy things. And one of the ways that we can tell the mass of a galaxy is by looking at how its gravity influences things around it, but also light. Gravitational lensing is when the gravity of an object causes the view of objects behind them to be distorted. Gravitational lensing really does work like a lens. When light passes through a lens, it gets bent, and that is what allows a lens to magnify things. It's bending the light, and gravity can bend light as well. The force of gravity can pull on the photons that are, trying to move through the gravitational field. Photons are very, very light, but they are still affected by gravity. A black hole is a black hole because it is pulling in all of the light. If light wasn't affected by gravity, then black holes wouldn't be able to pull in the light and stop it from coming out. So when we look at gravitational lensing, it is the gravity created by the mass of a galaxy distorting light, making things behind the galaxy appear closer, or at least distorting what they look like. I'm having a tough time finding good examples of this. For some reason, I do not have any good examples coming up. But thanks to gravitational lensing, we know that galaxies have a little bit more mass than we'd expect, or at least they appear to have more mass than we'd expect. So with galaxies, because of the way that they spin, because of the way that they rotate, and because of how galaxies distort the light of distant objects beyond them, there is a problem at what seems to be missing mass. If the universe, if physics works the way we expect it to, galaxies have way, way more mass than they should, or way more mass than we can see. And that's where dark matter and dark energy, mostly dark matter, come into play. Dark matter would help explain why galaxies rotate the way they rotate. If there was a lot of extra mass out at the edge of a galaxy, mass that we can't see because it only interacts with normal matter, with the stars, with the clouds of gas, in terms of gravity. It doesn't light up, it doesn't react with things. Photons seem to be able to pass straight through dark matter, but they do get distorted by its gravitational field. They can get pulled, but they don't actually crash into it. Gravitational lensing and the strange rotation of galaxies could be explained by dark matter, this extra matter that we don't really get to see, but it exists out there, somewhere. I'm looking for a good example of galaxies that do this, that undergo this effect. I know that there are a lot of galaxies out in the direction of the tail of Leo, but I don't know if any of these give examples of gravitational lensing. There are a lot of galaxies out here. There's a few more grand design. By observing their rotation, people have been able to see that they're rotating differently to what we'd expect. However, dark matter and dark energy would expect galaxies to form in pretty much the way we already thought they formed. Little bits of matter slowly gathering together, eventually building these big swirling clouds. So according to dark matter and dark energy, there is this other material in space that has a gravitational effect, but it is just stuff. It's just extra stuff that we can't see. Modified Newtonian dynamics instead says that gravity doesn't behave the way we expect it to. Gravity behaves normally when it's strong, when you're close to a star or close to a planet, but as gravity gets weaker, its behavior may change. The idea behind modified Newtonian dynamics is that we don't understand gravity, or that gravity doesn't behave the way Newtonian dynamics would predict. So the outer edges of the galaxy, because they're experiencing weaker gravity than the material in the middle, the weaker gravity has a different effect, causing the edges of the galaxy to sort of keep up with the center of the galaxy rather than falling behind in the way that traditional physics would predict. Modified Newtonian dynamics thinks, or it says, I suppose, that galaxies would form in a different way, that galaxies could in fact come together very quickly, because when gravity is weak, it's behaving differently. So in the early universe, when gravity was weaker, or generally weaker because there was less massed clusters of things, that it would allow the galaxies to form up much, much quicker. The reason I'm bringing all of this up, and the reason I am trying to talk about something that I can't actually show you in the sky, is because of new discoveries by the James Webb Space Telescope. The James Webb Space Telescope is able to see very early galaxies, and they are already bright and lit up. When we look into the early universe, we see lots of small galaxies that are, in fact, very well formed. Small galaxies, young galaxies that are already the shape that we'd expect from a galaxy. Nice, clear spirals. According to dark matter and dark energy, which was the prevalent theory, it was generally accepted dark matter and dark energy were likely to be correct. but the predictions that dark matter and dark energy made about the early universe haven't come true based on what the James Webb Space Telescope is seeing. The predictions made by modified Newtonian dynamics, which for a while was an alternative, a potential alternative to dark matter and dark energy that most people didn't think would actually be true, its prediction of how the early universe would look has come true. So even though dark matter and dark energy was seen as more likely for a while, the predictions it made haven't come true. And even though modified Newtonian dynamics, or MOND, was considered to be the less likely theory, its predictions do seem to have come true. So it looks like modified Newtonian dynamics is the way forward for now. It could turn out that gravity doesn't behave strangely when it gets weak. As of yet, we just don't know. And it can take a very long time to figure out the truth behind physics, figuring out how to test MOND, now that it seems likely to be the case. The general and special theories of relativity predicted the existence of gravitational waves, and 100 years later, the LIGO interferometer finally measured these gravitational waves. We may be waiting a while before we know for sure if MOND or dark matter and dark energy are the actual true things, and it may be some third option that we have yet to even conceive. But I hope that this video has given some sort of introduction to why dark matter and MOND are posited and why there is a controversy or excitement about them at the moment. I hope you enjoyed this video talking about stuff that we cannot actually see, and hopefully you will stick around for more videos in the future. If you would like to ensure more videos, make sure to subscribe to this YouTube channel and do like this video if you'd enjoyed it. You can also read some of this information on my website, queeveenscontent.ie. So thank you for watching, and hopefully I'll see you back here next time.